Right now, while your car sits perfectly still at a red light, there is a single contaminated sensor quietly strangling airflow, spiking fuel consumption, and accelerating engine wear without a single warning appearing on your dashboard. Mechanics ask this every week. How can a sensor the size of a quarter cause violent idle shaking, random stalling, and catastrophic engine damage all at the same time? Professional diagnostic shops witness this exact scenario constantly. The car comes in with a rough idle and poor throttle response. Spark plugs get changed. Fuel injectors get cleaned. Sometimes the entire throttle body assembly gets blamed. Nothing improves. The nightmare only stops when one sensor that most drivers have never even heard of finally gets serviced. And no, it is not the oxygen sensor. It is not the mass airflow sensor. There is a hidden component tucked behind the throttle plate that accumulates carbon deposits for years, disrupts the engine's ability to breathe at idle, and slowly transforms a smooth-running car into an unreliable mess that mechanics struggle to diagnose. Throughout this video, we are exposing the idle control system's darkest secrets, one component at a time. But the sensor that fails most predictably causes the most violent symptoms and can be restored to perfect function in under an hour appears at the very end. Number 8. The idle air control valve. The idle air control valve is the gatekeeper of your engine's survival at idle. When your foot comes off the accelerator and the throttle plate snaps shut, the engine would immediately stall without a controlled bypass path for air. That is exactly what the IAC provides. It is a motorized valve positioned to allow a precise amount of air to flow around the closed throttle plate directly into the intake manifold. The engine control unit constantly adjusts this valve's position based on engine temperature, electrical load, and accessory demand. Cold engines need more air to maintain 1,200 RPM. Hot engines drop to 650 or 700 RPM. When you turn on the air conditioning or headlights, the engine control unit commands the IAC to open slightly more. The destruction begins when carbon deposits from blow-by gases, oil vapor, and fuel residue accumulate on the valve's precision pintle or inside the tiny air passages surrounding it. These passages are often no larger than a pencil in diameter. Even a thin layer of buildup chokes airflow dramatically. The engine control unit tries to compensate by commanding the valve fully open, but contamination has already reduced its range of motion. The result is brutal. Idle speed hunts violently up and down, surging between 500 and 1,500 RPM with no pattern. The engine stumbles or stalls completely when coming to a stop. Cold starts become a gamble, and hot restarts after shutting down often require multiple attempts with the gas pedal pressed. In real-world diagnostics, roughly 60% of chronic rough idle complaints traced back to idle control issues are not electrical failures. They are carbon contamination. Proper restoration requires complete removal, disassembly if possible, and aggressive cleaning with carburetor cleaner or dedicated throttle body cleaner. But the IAC valve is only half the idle control story. There is another component that works in perfect harmony with it, and when it fails, idle quality collapses even faster. Number 7. The throttle position sensor. The throttle position sensor is the engine control unit's only way of knowing what the driver's right foot is requesting. Mounted directly to the throttle shaft, it is a precision potentiometer that translates throttle blade angle into voltage. At idle, with the throttle fully closed, output sits around 0.5 volts. As the blade opens, voltage climbs smoothly to 4.5 volts. This signal defines the boundary between idle control and normal driving. When the throttle position sensor reports closed throttle, the engine control unit hands control to the idle air control valve. The moment throttle angle increases, the engine control unit switches strategies instantly. Problems surface when the resistive track inside the sensor wears out at the critical idle position, because that is where the wiper sits during city driving and long red lights. It is the first spot to develop dead zones. When the throttle position sensor signal becomes erratic right at idle, the engine control unit cannot tell if you are asking for power or trying to coast. Fuel delivery becomes unstable. Ignition timing jumps unpredictably. The idle air control valve fights a losing battle trying to stabilize an engine the computer cannot even read correctly. Drivers experience sudden RPM drops that feel like the engine is about to die. Throttle tip in becomes jerky and unresponsive. Deceleration causes momentary hesitation or stumbling, and in severe cases, the engine actually shuts off during coasting because the engine control unit misinterprets throttle position and kills fuel delivery. Diagnostics reveal this instantly on a scan tool. Graphing throttle position sensor voltage while slowly opening the throttle shows sudden jumps, dropouts, or flat lines at specific angles. Most commonly, this happens right near closed throttle. Exactly where smooth idle depends on clean data. But idle quality does not just depend on how much air enters the engine. It also depends on how accurately the engine measures that air once it is inside. And that is where the next sensor becomes absolutely critical. Number 6. The Manifold Absolute Pressure Sensor, commonly called the MAP sensor. The MAP sensor provides the engine control unit with real-time data on intake manifold vacuum and pressure. Unlike a mass airflow sensor that measures air volume before it enters, the MAP reads absolute pressure inside the manifold after the throttle. This tells the engine control unit the engine load with extreme precision. At idle, intake vacuum is high. Manifold pressure typically reads 20 to 30 kilopascals, well below atmospheric. The engine is barely breathing. Under hard acceleration, with the throttle wide open, vacuum collapses and manifold pressure rises toward atmospheric, approaching 100 kilopascals at sea level. The engine control unit uses this data alongside engine speed and intake air temperature to calculate exactly how much fuel to inject. Idle becomes chaotic when the MAP vacuum reference port gets clogged with carbon, or when the vacuum hose connecting it to the manifold develops even a pinhole leak. A leak allows unmetered air into the system, falsely raising manifold pressure readings. The engine control unit interprets this as increased load and dumps in extra fuel. Idle becomes rich, unstable, and often accompanied by black smoke. Carbon buildup inside the sensor port has the opposite effect. It creates a restriction that delays pressure changes. The engine control unit receives sluggish, inaccurate data. Fuel delivery lags behind reality. Idle surges as the computer chases a moving target it can never catch. And here is the frustrating part. MAP sensor codes rarely appear until the sensor completely fails. Slow drift and contamination-induced errors sit just below the threshold that triggers a check engine light, silently destroying idle quality for months. Cleaning the MAP and inspecting every inch of vacuum line solves the majority of these issues. But even with perfect air metering, idle can still fall apart if the engine does not know its own temperature. That is where the next sensor takes over. Number 5. The Engine Coolant Temperature Sensor. This sensor is the ECU, the Electronic Control Unit, thermometer, determining whether the engine needs cold start enrichment or normal hot idle fueling. Mounted in the coolant passage, it is a thermistor that changes electrical resistance as temperature changes. When the engine is cold, resistance is high. The ECU responds by richening the fuel mixture dramatically and commanding the idle air control valve to hold RPM around 1,200. As coolant warms, resistance drops, and the ECU gradually leans the mixture while lowering idle speed toward 700 RPM. Idle catastrophe strikes when this sensor becomes contaminated or corroded. If the ECU believes the engine is permanently cold, it will keep dumping excess fuel even at full operating temperature. Idle becomes absurdly rich. Fuel economy tanks. Spark plugs foul rapidly, and the engine runs hot because cooling fans never activate. The opposite failure is equally destructive. If the sensor reports the engine is permanently hot, cold starts become nearly impossible. The ECU injects too little fuel for a cold engine. The starter cranks and cranks while the engine refuses to fire. Once running, idle speed stays too low during warm-up, causing constant stalling. And because the ECU never commands high idle, the engine struggles under the load of power steering, alternator, and AC compressor during the critical first few minutes. Cleaning the electrical terminals and connector is often enough to restore proper function. Oxidation, particularly the green corrosion common on older vehicles, creates enough resistance to shift the voltage signal and confuse the ECU. But if internal calibration has drifted, replacement is the only fix. And always verify proper coolant level and bleeding after removing the sensor. Air pockets in the cooling system will cause new temperature instability that mimics a bad sensor. Now we shift from temperature sensing to the most overlooked idle destroyer, a sensor so subtle in its failure that most drivers never suspect it until diagnosis forces the truth into the open. Number 4. The intake air temperature sensor. The intake air temperature sensor, known as the IAT, measures incoming air temperature, giving the ECU critical data about air density. Cold air is dense and oxygen-rich, requiring more fuel. Hot air is thin and oxygen-poor, requiring less. At idle, this matters more than most people realize because idle mixture tolerances are incredibly tight. The IAT is often integrated into the mass airflow sensor housing, but in many vehicles it is a standalone thermistor mounted in the intake manifold, air filter box, or intake tube. Like the coolant temperature sensor, it works by changing resistance as temperature changes. The ECU reads this resistance as voltage and adjusts fuel delivery accordingly. Idle becomes unpredictable when this sensor gets coated with oil vapor from the PCV system, fine dust that bypasses the air filter, or general intake system contamination. A dirty IAT reads incorrectly. If it reports air as colder than reality, the ECU overfuels. Idle becomes rich and unstable. If it reports air as hotter than reality, the ECU underfuels. Idle becomes lean, rough, and prone to stumbling. The cruelest part is inconsistency, because intake air temperature fluctuates with weather, engine bay heat, and driving conditions. A contaminated IAT causes symptoms that come and go seemingly at random. The car idles beautifully on a cool morning, then stumbles violently during a hot afternoon. Drivers blame fuel quality, humidity, or mystery gremlins. Mechanics chase ghosts. Nobody thinks to clean a sensor that looks fine from the outside. Cleaning requires extreme care. The thermistor element is incredibly delicate. No brushes, no abrasives, no compressed air blasts. Use only electronic safe contact cleaner applied gently, allow it to evaporate completely, then reinstall the sensor. Done correctly, this 5-minute procedure can eliminate idle issues that have plagued a car for years. But intake air temperature and engine coolant temperature together still cannot stabilize idle if the engine cannot control ignition timing properly. That requires one sensor most people associate with performance, not idle quality. Number 3. The knock sensor. The knock sensor listens for detonation, the destructive pinging that occurs when fuel ignites prematurely. It is mounted on the engine block, and it acts like a piezoelectric microphone tuned to detect knock events. When knock is detected, the engine control unit instantly retards ignition timing to prevent engine damage. But when the knock sensor becomes contaminated, develops a poor ground, or the mounting bolt loosens, it can send false signals. The control unit then believes the engine is knocking constantly, even at idle, and pulls timing aggressively. Retarded ignition timing at idle has brutal consequences. Combustion efficiency collapses. The engine struggles to maintain stable engine speed. Idle becomes rough. Fuel consumption spikes. And in extreme cases, the engine misfires intermittently, further confusing the control unit. What makes this insidious is that knock sensor codes often do not appear until the sensor fails completely. A sensor reporting false low-level knock will quietly destroy idle quality without ever illuminating the check engine light. Cleaning the sensor, ensuring proper torque on the mounting bolt, and verifying a solid electrical ground restores normal timing control and transforms idle behavior immediately. Now we approach the most common idle destroyer, a component that every driver interacts with thousands of times, but almost nobody cleans until it is too late. Number 2, the throttle body itself. The throttle body is where air enters the engine. Inside sits the throttle plate, a butterfly valve that opens and closes based on accelerator pedal position. At idle, the plate is nearly closed, allowing only a small, controlled amount of air past its edges. Carbon accumulation on the throttle plate and bore is inevitable. It comes from blow-by gases, oil vapor, and fuel residue. Over time, carbon builds up on the backside of the throttle plate. Even a thin coating disrupts airflow dramatically. As carbon accumulates, the effective idle air passage shrinks. The engine control unit compensates by opening the idle air control valve further. Eventually, the idle air control valve reaches its maximum range. Idle speed drops and the engine stumbles. Cold starts require holding the gas pedal. Cleaning the throttle body is straightforward. Remove the intake tube. Spray throttle body cleaner directly onto the plate and into the bore. Use a soft brush to wipe away carbon. Some vehicles require engine control unit relearning procedures after cleaning. But there's one final sensor, the true silent killer at idle, a component so critical that its failure can mimic every other idle problem simultaneously. And it's the one almost nobody checks until every other possibility is exhausted. Number 1. The crankshaft position sensor. Without a functioning crankshaft position sensor, the engine is completely blind. This sensor sits near the crankshaft, reading a toothed reluctor wheel. Every time a tooth passes the sensor tip, it generates a voltage pulse. The engine control unit uses these pulses to determine crankshaft position and engine revolutions per minute with microsecond precision. This data controls ignition timing, fuel injection timing, and idle air control strategies. At idle, the crankshaft sensor signal becomes critical, because variations of even 20 to 30 revolutions per minute must be detected instantly. When this sensor accumulates metal shavings, burnt oil residue, or road grime, the signal degrades. The engine control unit starts missing pulses. It miscalculates engine speed. Ignition timing becomes erratic. The result at idle is catastrophic. Engine revolutions per minute surge and drop violently. The engine misfires randomly, and in worst cases, the engine stalls completely. Here's the nightmare. A contaminated crankshaft position sensor causes intermittent failures that come and go with temperature. The engine idles perfectly when cold. Once warmed up, idle becomes violent. Drivers describe it as the engine shaking itself apart. Mechanics replace ignition coils, fuel injectors, even fuel pumps, chasing symptoms that vanish when the engine cools. Cleaning this sensor is simple but often overlooked. Locate it, usually near the crankshaft pulley or the flywheel. Unplug the connector, remove the mounting bolt. Pull the sensor out carefully. The tip will often be covered in metallic debris, oil sludge, or carbon. Use electrical contact cleaner and a lint-free cloth to clean the sensing tip and the area around the reluctor wheel. Reinstall with proper torque. The transformation is immediate. Idle smooths out. Engine revolutions per minute stabilize. The engine finally breathes the way it was designed to. The pattern across all these sensors is identical. They fail slowly, silently, and without drama. No catastrophic breakdowns, no sudden warning lights, just a gradual descent into rough idle, poor fuel economy, and driver frustration. Because idle problems feel vague and inconsistent, they are often the last issues drivers pay attention to, until the car becomes genuinely unreliable. But you are different now. You understand that idle quality is not a mystery. It is the result of clean sensors, proper airflow, and an engine control unit receiving accurate data. The moment any sensor in this system starts lying, idle falls apart, and the solution is almost never replacement. It is maintenance. Cleaning electrical terminals, removing carbon deposits, restoring proper signal paths. Before you drive away assuming your rough idle is normal aging, check these sensors. Clean the throttle body. Inspect the idle air control valve. Verify the crankshaft position sensor is free of contamination. These simple steps, done properly, can restore idle quality that rivals a brand new car. And if you want to learn the next hidden system that silently destroys engine reliability while mechanics keep replacing the wrong parts, subscribe now. The next video exposes a fuel system secret that costs drivers thousands in wasted repairs every single year.